For this problem, I'm looking for the coefficient of friction between the skis and the ground. And I have a person standing on the skis being pulled by the dog, so we're going to kind of combine the person and the skis all as one body. And for this problem, I'm going to draw two free body diagrams, not just one. The first free body diagram is going to have all the forces without any components. The second free body diagram is going to have the forces with components for tension. And the reason why I'm doing that is to make it clear what's going on in the problem in the first free body diagram, and the second free body diagram is what we're going to use to actually solve the problem. And because the tension isn't parallel and perpendicular to the other forces, we need to find its components. So let's start with the free body diagram. All right. So here's the skis and the skier. That's the body itself. Let's see, what do I have acting on this? I'm going to need kind of a dotted line here, so let's just kind of hand draw a dotted line. And I'll have a normal force going up, so the ground is acting on the skier, pushing it up, keep it from going down, so that's going to be the normal force. I'm going to use the Greek letter eta, representing the normal force. The dog and the skier are moving from left to right, so our friction is going to go parallel to the surface and opposite the direction of motion. So I'll represent that with a cursive F. And let's see, and of course I have the earth pulling due to gravity on the skier and skis. That's going down, so that's acting on the skier. So that's going to be the weight. I'm going to actually be using mg in all my equations. And I'm doing that because I told me the student's equal to 90 kilograms, so I'll make it a little bit easier later. And finally, I've got this pull going on here. So this pull, I'm thinking I wish I drew my free body diagram a little bit larger. So let's just kind of exaggerate that a little bit. It's going to be like that. That's going to be our tension on the rope, or on the leash actually, for the free body diagram for the skier. All right, so that's my first free body diagram. My second free body diagram is going to be a copy of this one, with an exception. So I'll have a normal force going up. There's the normal force. I'll have friction going the opposite direction here. Friction, I'm going to have the weight, which I'm going to call mg down here. And then I've got my tension going off here, like my 30-degree angle. It's not quite right, but it'll work. And that'll be the tension. Notice how all my labels are close to the tips of all the arrows. That's just making it easy to put the other math on here. The other math I need to do, and I'm going to do this in red just to make it kind of stand out a little bit. I'm going to break this up into components, going over and going down. So when I'm doing components, I need to make sure that they follow the rules of vector addition. And in vector addition, the vectors add tip to tail. So when I'm doing it, t is basically the resultant, and I start at the tail of t, that's where the red is, and it goes over, and then it's going to go down to create my right triangle, and they connect tip to tail when they do that. And it ends up at the same place that the resultant does. It doesn't make like a circle going around or a cycle. It seems to go around a loop. Both combinations end up at the same place. All right, so mathematically, I know one thing. Oh, I should have included this in my original diagram. This is 35 degrees, and this is 35 degrees. Now let's go back to what I have. This is going to be t, and this is the adjacent side to the 35 degrees. That's going to be the cosine function. And the opposite side, the one that's vertical, that's going to be t, and that's opposite of the 35, so that's going to be sine 35 degrees. So this is going to be the free body diagram I'm going to use to set up and solve for everything. In a blink of an eye, I've moved everything over and got rid of the original free body diagram so I could conserve some space here. All right, so I'm going to sum up the forces in the x and y direction. Now that I have these red vectors, what I'm not going to use anymore is I'm not going to use this right here. So I'm not going to use the tension. I'm done with that. And I'm going to let that represent by the red vectors in the horizontal and vertical directions. All right, so let's sum up the forces here. So I'm going to sum up the forces in the x direction. It's either changing speed or not in the x direction. In this case, it tells me that it's moving in a constant velocity up here. So because it tells me it's moving at a constant velocity, I know that there's no change in speed. So summing up the force in the x direction is going to be equal to 0. And then I'll make all the forces going to the right minus all the forces going to the left. So that's going to be t cosine 35 degrees minus friction, which I have a cursive F for friction. And those are only two forces horizontally. Vertically, I'll sum up the forces in the y direction, and that's going to equal 0, again, because I'm not changing speed in the y direction. and that's going to equal all the forces going up minus all the forces going down. So eta minus mg minus t sine 35 degrees. So there were two forces in this case going down. That's why I had subtracted them both. All right, so at this point, this gives me a couple different equations. This is going to give me that, let's see, I'll use the top line, sum of the forces in the x direction. So I'm going to say friction is equal to t cosine 35. And the second one I'll use is from the sum of the forces in the y direction. And that's going to say that eta is equal to mg plus t sine 35 degrees. So I'll call that equation 1 and equation 2 just to make it easy to talk about what's going on. All right, so once you get past the summations, really the rest of it is just math, and that means that there's multiple ways of finding the correct answer. So I'm just going to show you one of the ways of finding the correct answer. What I'm going to do is I'm going to take the friction and I'm going to replace friction with the definition of friction. So the definition of friction is that friction is equal to mu times eta. So I'm going to replace my friction with that. So I'm going to take equation 1 and I'm going to say that, let's see, mu times eta is equal to t cosine 35. Now I'm solving for mu, so I'm going to go ahead and just isolate mu right now because math looks pretty easy. T cosine 35 divided by eta. Let's see, let's label these equations 3 and 4 just to make talking about them easy. The next thing I'm going to do is I'm going to take equation 4, the numerator for eta, and I'm going to replace it with what eta equals in equation 2. So that means that eta is equal to t cosine 35 divided by everything that eta is equal to in equation 2. That's going to be mg plus t sine 35 degrees. There we go. All right, all set. So, oops, sorry about my screen. Therefore, mu. Now I'm going to put in numbers. Notice I didn't put any numbers in until now except for the angle. So now I'm going to put in my numbers. That's going to be 600 newtons cosine 35 degrees divided by mg. So that's going to be 90 kilograms times 9.8 meters per second squared on the Earth, meters per second squared, plus my tension, 600 newtons. It's supposed to be an N. That's kind of funky. Times sine 35. And it's a fraction. When I do all this, mu comes out to be 0.401 for the coefficient of friction. If you didn't get 0.401, check on a couple things. Make sure your calculator is in the degree mode when you're doing all the calculations and not the radian mode. The other thing to look at is in the bottom, sometimes people forget to put the whole denominator in parentheses when they're dividing it. So they might say 600 cosine 35 divided by, and then they don't put parentheses for the whole denominator, so it doesn't do the right order of operations. So pay attention to that.